All right, our last set of 3 problems, we're going to look at 7, 8, 9. We're going to wrap this up. 7 and 8 are both center of mass problems. And I explain center of mass in the notes. I also explain center of mass in the lecture video. Center of mass, there's no problem solving involved. It's just number crunching. It's just a calculation. The idea of center of mass is it's the average position of the mass. So there's a couple principles that go along with center of mass. I'll talk about them more when we get to problem 8. But for problem 7, it just says 4 objects are on the y-axis, and they give you the y-coordinates. It's kind of silly. They give you the y-coordinates, and then they ask you for the x and y coordinates of the center of mass. So I'm going to go ahead and draw what they're giving here. So this is problem 7. I'm going to draw your y-axis like so, and x-axis that way. And I'm just going to call them M1, M2, M3, M4, along with Y1, Y2, Y3, Y4. So they do something like this. They go something like, okay, so here's M1, and it's at Y1. That's its position. And then here's M2, and it's at Y2. And then one of them's at the origin. So M3 is at the origin. Y3 is equal to 0. And then the last one is at some sort of negative bit down here. So this is going to be Y4 and M4. And the idea, again, is that the center of mass, these are all different masses, but the center of mass is the average of their positions. It's the center of the mass, right? So we're simply going to calculate the average of these positions. But let's talk about x first, because center of mass is often a very simple thing to just look at and identify. The x position of all of these guys is x equals 0, right? So where is the average x position of all of these? It's at x equals 0. Here's another way to look at it. If we had several masses that were here, 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 you know the center of mass has to be somewhere in the middle of these guys. That's how averages work. It's like in the average. So you know the center of mass is in between these guys somewhere. Well, if they're all in a line, that means the center of mass has to be on that line. You can't have these guys here and the center of mass is over to the side. It doesn't make sense. So, very simple. All of these guys are on the y-axis. The x-coordinate of the center of mass is 0. My goodness, it's silly. But you've run into this before with some questions they've asked. Punch a 0 in, get your green check, move on. How do we get the y-coordinate of the center of mass? Well, I talk about this in the notes, and I also talk about it in the lecture video. We get the y-coordinate by taking the average of the positions. Now, normally that would be add the positions and divide by 4. That is what you would do if the masses were all the same. But center of mass is not a direct average, it's a weighted average. And the weighted average is M1, Y1, M2, Y2, M3, Y3, M4, Y4. You basically have to consider each mass times its position. There's no problem solving here, it's just number crunching. Just add them all up, divide by the total mass. In essence, by dividing by the total mass, you're getting the average of the positions, but the importance of each position is weighted by the amount of mass that's there. All right, that one's done. So problem 8, I talk about this idea in the lecture video where I talk about center of mass. They're giving you this kind of thing. They're giving you we're going to go here. I'm going to try and recreate this thing best I can. Freehand, Shies. Okay. So here we go. They're giving you this steel plate that is basically a collection of 6 squares. And they say both axes are marked in increments of, mine says 8, yours is going to say something different. But basically, you're going to have increments here, 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 here. And they say, find the x and y coordinates. If this is your y-axis, and this is your x-axis. Find the x and y coordinates of the center of mass. So you know it's going to be somewhere. Notice this thing is heavier toward the bottom, right? And it's also heavier toward the left. That means if the center of this thing is right here, the center of mass is going to be more toward the bottom and more toward the left. So it's probably going to be like there or so, I don't know. But you can calculate it. How do you do that? Exactly the same way we did here. We're going to take advantage of a simple principle of center of mass. If you have a symmetrical object, that symmetrical object can be treated as if all of its mass is at its center. So here's what we do for this problem. We chop this steel sheet into symmetrical pieces. That's how you do center of mass calculations of something like this. So, what symmetrical pieces? The squares. We're going to take all the mass of this square and put it right here. So this guy has mass m, and we're going to take all this mass and put it here at this point. Then we're going to do the same thing for this square, this square, this square, this square, and this square. What do you now do then for these 6 squares? Get their coordinates. So this square is going to be at x1, y1. This square is going to be x2, y2. This one, of course, keep going, x3, y3. This one will make x4, y4. It doesn't matter what order you put them in. This one, x5, y5. And this guy, we'll call it x6, y6. What do? Get the x coordinates of each, get the y coordinates of each. Now what do you notice? All 3 of these are at the same x coordinate. Whatever your marker is here, that's just half of it because it's in the middle. So these guys all have the same x coordinate. These 2 have the same x coordinate. These 3 have the same y coordinate. These 2 have the same y coordinate. Jot down your coordinates. And then how do you find x center of mass? You do the same thing you did here. X center of mass is going to be equal to m times x1 plus m times x2 plus m times x3 plus divided by, what's the total mass? It's just 6m. Here we catch a little bit of a break. Because we divided this into identical pieces, then the center of mass is just the average of the 6 positions. Because we get m, m, m for each piece, and we divide by the total mass, you could just divide out m, and what you get is the 6 coordinates divided by 6. Do the same thing for the y's. You're done. So in this case, because they all had the same mass, it was a simple average of the 6 positions. That's it for center of mass. We're not doing anything else more. It's a pretty simple idea. Just like our graph problems, I just wanted to throw a couple of these at you just so that it was planted in your brain. Once you do 2 of them, that should be enough to go, okay, I know how to do this. All right, that's 7 and 8. Let's wrap up with number 9. And we will put chapter 8 behind us. Number 9 has a 12-gram bullet fired into a 2.8 kilogram block, initially at rest on the edge of a frictionless table of height 1 meter. The bullet remains in the block, and after impact, the block lands 2 meters from the bottom of the table. Determine the initial speed of the bullet. What do you want? Oh boy. Uh-oh. Trouble's coming. All right. I'll get this done, and I'll deal with trouble. So they're giving you a picture. It looks like this. This is number 9. We've got a block here. The block is about to get hit by a bullet. So this is going to be picture 1. What are we going to have? There's going to be a collision. Bullet hitting block is a collision. Now recall when I talked about the softball problem and the baseball problem, softball problem way back when, I said the bat hitting the softball is not a collision because the batter is holding the bat. The bat is not free to move in response to the ball hitting it. So, to qualify as a collision, the 2 objects, when they collide, they have to both be free to move in response to that collision. That's what qualifies a collision. This bullet, free to move, right? The block, free to move. This is a collision, just like our train cars, just like the blocks in problem 4, just like the sticky clay in the block. Those all qualify as collisions. So I'm going to have little m here. I'm going to call this guy big M. And of course, his speed is 0. I'm going to go ahead and call this v1. And v1's unknown. I believe that's what they want you to find. What happens here? Collision, and then he goes projectile. So what do we need if it's a collision? This is going to be picture 1. I'm going to call this picture number 1. But we need, this is immediately before. Follow the rules. We need a picture immediately after. I'll go ahead and draw it right here. What's immediately after look like? Hasn't moved yet, right? But we've got something like this, and now they are going to have speed v2, and that's also unknown. So this guy is now moving, right? But, just like I talked about before, hasn't gone anywhere yet. So this is going to be picture 2 immediately after. Let's see if I can do that. Sorry about the spacing. What happens then? Well, then he becomes a projectile. And so we have a combo problem. Our combo problems before were energy, then collision. Maybe energy, then collision, then energy. Or maybe just collision, then energy. But we saw energy when we had one object changing its speed, maybe changing its height. There was some friction involved. Now, we have a combo problem. Somehow this guy got taller. I don't know why that happened. Sorry. But it's collision and then projectile motion. And this is the point in the semester where you should start being able to recognize what kind of problem you're working with and if there's multiple problems involved. We've only done 5 things. Kinematics, chapter 2 and 3. Forces. Energy. Oh, I'm sorry, what am I saying? We've only done 4 things. Oops. Kinematics. Forces. Energy. Collisions. Those are the list of things, list of types of problems that you will see, that we will deal with. That's it. Kinematics is position, velocity, acceleration, and time. Forces, right? Forces involve acceleration. Energy involves speed. Collisions, 2 things colliding. That is it. That is all we have done this semester. And it's essentially all we're going to do for the entire semester. 4 simple things. What happens here? It's projectile motion. What do? You should know how to do a projectile motion problem. I'm going to need an origin down here. I'm going to need out here, I'm going to need d, 0. Up here, I'm going to need 0, h. I'm going to need a y-axis. I'm going to need a y-axis. I'm going to need an x-axis. This is picture 3. Picture 1, picture 2, picture 3. Label your coordinates. Label your speed. So this is going to be v0. But what do you know about v2 and v0? They are the same thing. We're transitioning from collision problem to projectile motion problem. This velocity is the same as this velocity. Incidentally, there is a problem on the homework, homework 2, in which Tarzan is swinging and then the vine breaks and he becomes projectile. And so you have v0 for Tarzan, but you also have v while he is at the bottom of his swing on the vine. They are the same. It is the same idea, right? Initial velocity of the projectile motion is the velocity in this picture. Same thing for Tarzan on the homework. All right. So what do I do with this? I need to label time, right? There's no angle because he's going horizontally. So what do? Make my table. X, Y, right? Final position. Initial position. Initial velocity. Acceleration. What do you have for final position? D, 0, 0, H, V0, 0, and then 0 minus G. You should be able to recognize this as exactly the same as several problems we've already done, including our very, very first projectile motion problem when the beer mug hit the floor. This is exactly the same situation. When the beer mug hit the floor, they said, find V0, and T was the other unknown. What do? Write your 2 equations, get your time, get V0. So from this, you can get T, you can get V0. But what do you know? You know V0 is the same as v2. v2 is the speed at which it leaves. Now what do you have here? Going from 1 to 2, we have a collision. So what can we write for our collision? Momentum before equals momentum after. What is your momentum before the collision? It's mv1. What is your momentum after the collision? They are together. So we have little m plus big M times v2. You have v2. You got to sort of work backwards. The projectile motion gives you v2. You have v2, you got the masses. Calculate your v1, you're done. And we're done. Chapter 8. That's it. All right. I'm going to turn it off. See you guys next time.